Hi guys, welcome to today's lecture. Today, first I will provide you the summary of the topics that we have covered so far. Then we will see some more discussions on the simple linear regression. So far, we know that in statistics, we are concerned with questions that need data to be answered. And answering those questions using data, we use a route map called a statistical process. The statistical process starts with specifying questions of interest, specifying target population and statistical variables of interest, collecting data on those variables of interest either from the target population or from a target sample, then data management, data organization, data cleaning, and then data analysis and interpretation. Data analysis is a central step in the statistical process, and much of statistics courses are devoted to study different data analysis techniques. Data analysis techniques are generally divided into two parts: descriptive analysis techniques, which are used for both population and sample, and inferential analysis techniques, which are only used when the data come from sample. We have started our exploration of statistical data analysis with univariate descriptive techniques, namely frequency table and frequency distribution for both qualitative and quantitative variables, different graphical analysis techniques for both qualitative and quantitative variables, different numerical techniques such as measures of location, measures of variation, and measures of distribution. Then we have covered an important concept of subsample analysis, and we have seen that subsample in two ways: random subsampling, where we randomly select some observations from the sample, or we subsample based on a predefined condition. If you recall, subsampling based on a predefined condition, then analyzing subsamples is actually a bivariate analysis, because there practically we have two variables involved. Then we have moved on to a new chapter of bivariate analysis. The main idea behind bivariate analysis is to study the association between two given variables, and I hope that you know what association means. Then we have covered different bivariate analysis techniques such as two-way tables in 3 different cases, bivariate graphical analysis techniques in 4 different cases, and bivariate numerical techniques in 3 different cases. Now the question is, what is next? How we can extend our knowledge of bivariate. This we will see in the next lecture, but first let's see some more discussions on simple linear regression. Simple linear regression, or SLR, introduced last lecture to study the relationship between, or the association between, two quantitative variables. If we have two quantitative variables x and y, and we want to study the association between the two, one option is to use simple linear regression. For that, first we need to have the scatter plot of the two and compute the correlation. Considering the scatter plot and correlation, if we were satisfied that we can, based on the scatter plot and the value of the correlation, if we decide to model the association between the two variables using a linear fit, we need to think of the following cases. First, are we concerned about the variation in one of the variables being explained by the variation in the second variable? If that is the question of interest, then in this case we use the first variable as a dependent variable and run the LM function in R and check the p-value and R squared. Two possibilities are there. If p-value is less than 0.05 or in some cases 0.1, then R squared is significant, and we can go ahead with the interpretation of the amount of variation in the first variable or dependent variable explained by the variation in the second variable. If the p-value is bigger than 0.05 or in some cases 0.1, then R squared is not significant. Second, if our question is concerning the amount of impact or the direction of impact of one of the variables on the second variable, in this case, based on a theory or hypothesis, we have to specify our dependent variable and then run the LM function of the dependent variable on the independent variable and check p-value of the estimated coefficients. If the p-value of the estimated coefficient is less than 0.05 or in some cases 0.1, then the impact is significant. Otherwise, the impact is not significant. If the impact was significant, we go ahead with interpretation of the impact of the independent variable on the dependent variable, both in terms of size and in terms of the direction. When it comes to significant impact, we have two types of significance: economic significance and statistical significance. Statistical significance is purely specified by the p-value, most of the time less than 0.05 of the coefficient. Economic significance is specified by both p-value and the size of the impact, or the size of the estimated coefficient. In simple linear regression, if you recall, we have defined a concept called residuals. Residuals are nothing but the difference between observed values and the fitted values. In order to produce the residuals, we use a function called augment, which comes under a package called prom in R. The larger the residuals, in other words, the larger is the deviation of the observed values from the fitted line, the smaller is the linear relation. Okay, now let's see how we can implement those discussions which we had in the lecture note in R. First of all, I go ahead and specify my working directory, then call my dataset. Remember that for today's lecture, we need two packages, namely ggpopr and prom. Please install them before coming to the class. I have installed them and I go ahead and library them. Okay, the question is how much variation in evaluation grade is being explained by the variation in working hours. And the main question here is whether working hours of the employees it's important in their evaluation grade. For that, I go ahead with scatter plot first. I use ggplot2 like last time, run everything. Now you can see here the gray area around the line, around the fitted line, is very wide, and we know that the observed values, in other words these points, are very far from the fitted values, which is the blue line. In order to calculate the amount of correlation, I use the correlation, which is minus 0.09, which is 9%, very low correlation. Furthermore, I can check the significance of the correlation. Now you can see that the p-value of the correlation is 0.6, which is bigger than 0.1. Hence, we can conclude that the correlation between working hours and evaluation grade is not significant. Therefore, working hours cannot explain much of the evaluation. Second question, how much impact does salary have on expenses? This is a theoretical question actually. In economics, the theory says that as the income increases, the spending increases. As the income decreases, the spending decreases. Go ahead and sketch the scatter plot of the two, and I use the ggplot. Now you can see the gray area around the fitted line. It's very small, it's very tiny. Or we see that the points, the observed values are very close to the fitted values, which is on the blue line. Now I go ahead with the calculation of correlation. Correlation is 0.96, which is 96%, which is a very high correlation. I can test the significance of the correlation, p-value for which is 0, and it's an indication of significant correlation between the two. That means the impact of salary on expenses is very high. In order to see the amount of impact and the direction of impact, whether increasing salary would increase expenses or decrease the expenses, that's the direction of impact. The size of the impact is the value of the estimated coefficient. I use a lim function in summary. Now you can see here in this table I have the estimated coefficient of the salary, which is 0.75, and importantly the p-value of that, which is 0. Now I can say that the direction of impact of salary on expenses is positive. That means increasing salary will increase expenses, and the impact is significant because the p-value is 0. Next, let's see how we can study simple linear regression residuals. Why studying simple regression residuals? It's important because we want to see how far the observed values are from the fitted values. The fitted values is nothing but the linear regression line. I run the linear model function of expenses and salary. I call it L1, and then I store everything that this linear model produces in an object called M1 using the augment function. So augment. Now I use again ggplot in order to plot the residuals. I use, of course, this time M1 as my data set, where I have stored all outputs of the linear model N1, L1, and then X values, of course, again salary, Y values expenses. What I have added here is segment. Segment is showing the size of the residuals. And for that I use X axis again salary, but for Y axis I use the fitted line. So let me run all the things together. And now as you can see here, in the case of expenses and salary, these lines here, these are segment lines showing the amount of variation or the amount of residuals for each of them. Now let's see the same case with evaluation grade and working hours. I put everything in L2, N2, and G2 and F2, run everything together and see what happens. Now look here, previous to the first case, here the residuals are very, very large. You can see we have as large as this much. If you consider this observed value and the fitted value is here, now you see this much is the residuals. And generally, if you add all these residuals, you get much larger total residual here in this case. Now, if you want to compare the two, you use the function called ggarrange and put the two plots together and run it, and then you can compare. You can compare how residuals in the first case, where we have salary and expenses, are smaller than the residuals in the second case, where we have working hours and evaluation grade. And of course, we can easily see why linear relation between these variables here in the first case on the left side is much stronger than the case. If we decide to use a simple linear regression for our model for studying the association between two given variables, how can we write the output of the simple linear regression? We can use equations such as expenses hat here, which is the estimated or the fitted expenses equal to 1.98, which is intercept, and 1.21, which is the coefficient of the salary. N is the number of observations, R squared is the amount of variation, and expenses being explained by the salary. And most of the times in the reports, however, we use tables in the form.